Welcome you one and all for this session. International Conference, Materials, Manufacturing and Mechanical Engineering for Sustainable Development. My paper is on topic of mechanical and water absorption properties of Calotropis gigantea plant fiber reinforced polymer composites. My paper ID is 9135. Coming to the abstract, in this paper, utilization of natural fiber in polymer matrix composite materials for research purpose and industrial application has witnessed a steady growth during the recent times. But eventually we can see the various research work envisaged the benefit of using natural fiber as reinforcement in place of artificial fibers for the manufacturing of composites, and hence the current experiment work is focused in utilizing Calotropis gigantea fiber as a reinforcement for making composite materials. In this work, what we are going to do means we will take Calotropis gigantea fiber as reinforcement for making the composite material. When we are going for that composition of the composite material, we are using a compression molding method. Why we are going for that means compression molding method was used to fabricate the composite laminates, and they were subjected to water absorption and mechanical property testing such as flexural, tensile and impact testing. It was observed from the experimental result that water absorption and mechanical characteristics of Calotropis gigantea fiber reinforced composite were on par with the other natural fiber reinforced composites, which were experimented in the past literature surveys. Now we will move on to that step by step introduction part. We know that composite is a combination of two or more materials to get a better properties. This is a natural fiber reinforced composites. When we are going for the natural fiber reinforced composite, if we take this generally natural fiber from plants, alright, recently attracted much attention of the scientists, industrialists, engineers and researchers for their potential utilization as substitutes for synthetic fiber in fiber reinforced polymer composite materials. Okay, this is a major reason. And also we will have some specific benefits when we are going for a natural fiber, which is nothing but biodegradability, low cost, easy availability, non-abrasive nature, enhanced specific strength, mechanical characteristics and mainly environmental friendliness. This is most important. That's what we are going for, natural fiber reinforced composite. In the natural fiber reinforced composite, we will go for Calotropis gigantea bark fiber. You can see that several researchers investigated the potentiality of using two different types of Calotropis gigantea fiber. Normally, if you take the Calotropis gigantea plant, we can able to get two types of fiber. One from bark stem, another from seed. Alright, which is used as in reinforcement in composite material. If you take in the Calotropis gigantea fiber or extracted from bark for the plant, and these characteristics with smaller thickness when compared with diameter. Okay, this is very introduction level part. And when we move on to the LY556 epoxy resin and HY951 hardener, why we have to choose it? The reason behind the LY556 epoxy resin is a solvent resin. That's most important. And then it have a medium viscosity. When we are going for a composition laminates, the resin can able to freely move into throughout the entire laminate of composite because of medium viscosity. And then we are using a hardener HY951. The main reason because it gives high rigidity. That's what we want. Okay, it will give that. So that what we are using epoxy resin and hardener in a 50:50 ratios. And then when we are going for compression molding, okay, in compression molding it is a manufacturing method of composite laminates where the polymer matrix material is preheated before being placed in the mold cavity, which is open. Okay, and then we will go for this. Mainly when we are going for compression molding, the reason behind is if you take a lot of literature, they are doing a hand layup method. Okay, but when we are going for hand layup method, there is a drawback, that is when applying of some force during the composite laminates, it will distribute in ununiform manner. Some place it will be in higher amount of force. Okay, to overcome that we will go for compression molding. During the compression molding we will supply an uniform force. The stress will be acted in each and every place at a uniform manner. That's what the advantage here, and we will get a high quality of composite laminates from the compression molding. And then flexural test. If you are taking the flexural test, we are using ASTM D790/10 standard. As per the standard, we are going to take the specimen measurement, okay, length into breadth into thickness, which is 125 mm into 12.5 mm into 3 mm, and we take the gauge length during the specimen was adopted as 100 mm. Load cell of 10 kilonewton was used. Okay, normally we will take the rate of loading maybe 5 mm per minute. Okay, and then we will go for tensile test. In tensile test we are using ASTM standard D68/10. We are going to prepare a specimen, a dimension of 165 mm into 25 mm into 3 mm. Okay, and test was conducted in universal testing machine with a gauge length of 100 mm and 5 mm per minute as a cross head speed. Okay, and then we will go for impact test. Okay, in impact test we are using an ASTM standard 256/10 standard we are going to use. Okay, and the dimension of specimen is 62.5 mm into 12.5 mm into 3 mm. We are going to use it. Normally we will go for eyesight impact test. When we are going for an eyesight impact test was conducted, if you take means we have to calculate the impact strength, okay, in which the component specimen is mounted horizontally against a pendulum hammer with a swinging action. Okay, and then we will go for water absorption test. Okay, in water absorption test we are using ASTM standard ASTM D570. We are going to use it. What we are going to do means the specimen of the fiber and a composite was immersed in water for more than 72 hours. Okay, and change in weight of composite material is recorded every 4 hours. Okay, in a periodic manner we are going to record it. The percentage of weight gained, okay, the composite sample we have to calculate. How we are going to calculate means in a percentage weight gain. Okay, it's some equation. Okay, the percentage weight gain which is equal to wet weight minus initial dry weight by initial dry weight into 100. We will get the percentage of weight gain. Okay, later I will show in figure, you will get very clearly. Okay, and then we will go for fiber extraction. This is so interesting. Okay, this is the Calotropis gigantea plant. Okay, we have to remove the leaves, petioles, and then we will get Calotropis gigantea bark stem, like that you can see it. Okay, and then we will go for water heating process. What is the water heating process? After taking that bark stem, we will dip into water nearly for 7 to 8 days. Okay, during the days what it happens means the water molecules, okay, it's having capillary action now, okay, and it is able to penetrate into the stem. Okay, it will ooze out. Okay, it will get some bulgy like that. after some 8 days, we will take out the Calotropis gigantea bark stem and we will go for sunlight, okay, for 2 days. After that, the fibers will be slightly come out, okay, by mechanical process. Okay, you can see in figure, okay, like that we will extract the fiber, okay, in a mechanical manner. Okay, normally it's very light density, nearly 0.56 gram per cubic centimeter, okay, as per literature survey. Okay, and then we will get a cumulative manner of Calotropis gigantea bark fiber, okay, like that we will get it. Okay, this is the fiber, finally we will achieve it. Okay, and then we will move into that fabrication of composites. I am already told you we are going to use LY556 epoxy resin, okay, and then HY951 hardener. Okay, the main reason here is the epoxy resin is a medium viscosity and also solvent free. That what here. The hardener will give higher rigidity. Okay, that's what we are going to use, nearly 50:50 ratio. Finally, by using a compression molding machine, okay, we will apply the load, okay, and then we will pour the resin and the hardener in a mixture. Okay, finally we will get composite plate. Okay, from there you can see the figure 8. You can see this is the composite plate. When I am going for test, okay, I will take the flexural test. Okay, for that I will get 2 data. One is the flexural strength. You can see the figure. The flexural strength is vary from 60 megapascal to 80 megapascal. You can see that there is a 6 samples. Okay, we are taking a 6 samples from a single composite plate. Okay, we will take nearly 60 megapascal to 80 megapascal. It will be varying. Okay, you can see the graph. You can get it very clear manner. Okay, the sample 3 and the sample 2. Okay, what's a flexural strength? Why we have to calculate means the flexural strength is also known as modulus of rupture. Sometimes we call bend strength, fracture strength we will call it. It is defined as the stress in a material just before it yields in a flexural test. Okay, and then flexural modulus, that is in red color, you can see it is in a gigapascal. Okay, don't get confused. Flexural strength is a megapascal and a flexural modulus is a gigapascal. Okay, if you take the flexural modulus is nearly 6.55 gigapascal to 8.86 gigapascal. You are right. When we are going for flexural modulus, we will call it as bending modulus. Okay, it's an intensive property. Okay, the flexural modulus is nothing but the ratio of stress by strain when it going for a flexural deformation. Okay, it having tendency of a material to resist bending. Okay, that is the flexural modulus. Okay, and then when we are going for tensile test, we will get tensile strength and tensile modulus. The tensile strength is in blue color, you can see, is vary from 41 megapascal to 58 megapascal. Okay, if you take in the tensile strength, the maximum load that a material can support without fracture. Okay, maximum load that a material can support without fracture when being stretched, okay, divided by the original cross section area of that material, that is the tensile strength. We have to calculate it. Okay, nearly 41 megapascal to 58 megapascal. And tensile modulus, you can see we will get nearly 212 megapascal to 292 megapascal. Okay, when we are going for tensile modulus, is a ratio of stress along an axis to strain along that axis. Okay, if you see, you guys know what is a stress. Okay, stress is nothing but force by unit area. When we are going for strain, is a ratio of deformation over initial length. Okay, these are basic level. Okay, we will get nearly 212 megapascal to 292 megapascal as the tensile modulus. When we are going to increase the fiber content, okay, we have to achieve a greater tensile strength and tensile modulus. Okay, and also length of fiber will play a vital role. Okay, this is also very important. Okay, the fiber content is plays a very vital role. And coming back to impact strength, the highest impact, okay, the highest impact energy absorbed by Calotropis gigantea fiber composite is 10.4 kilojoule per meter square. Okay, and then lowest impact energy absorbed by Calotropis gigantea fiber composite is 8.8 kilojoule per meter square. Okay, we have to calculate it. Okay, and then finally we will go for water absorption test. Okay, you can see the blue color is the Calotropis gigantea fiber and red color is the Calotropis gigantea fiber composites. You can see what we are going to do in water absorption means by increasing the time, okay, the weight gain percentage is increasing. Okay, you can see the graph gradually is increasing. Okay, but when comparing with Calotropis gigantea fiber, okay, this is a blue, okay, and red is the Calotropis gigantea composites. Okay, the Calotropis gigantea fiber observing higher amount of water molecules. Okay, the reason behind is generally whatever it may be, okay, natural fiber having a hydrophilic nature. Okay, due to the hydrophilic nature, the Calotropis gigantea fiber have the tendency to absorb n number of water molecules when compared with the Calotropis gigantea fiber composites. Okay, we will take the 72 hours totally. Okay, we will take a reading, we will record a reading for periodically 4 hours basis. Okay, we are used the water absorption tester machine. Okay, we used. Okay, and then finally come to the conclusion. Tensile strength and modulus were found to be better for Calotropis gigantea fiber composite due to enhanced load carrying capacity of Calotropis gigantea fiber. Second point is the Calotropis gigantea fiber reinforced composite material exhibited better flexural strength and modulus value of 87.88 megapascal and 8.86 gigapascal respectively. Third point is the maximum impact strength its recorded is nearly 10.4 kilojoule meter square. Okay, and then from the experiment it is concluded that the rate of water absorption of Calotropis gigantea fiber is higher than the composites. This may due to the hydrophilic nature. Okay, I am already explained it. Overall, final conclusion, it could be stated that Calotropis gigantea fiber reinforced polymer composites are very efficient materials and substitute that are much suited for various applications in domestic, automotive, it may be in interior or exterior components. Okay, thank you one and all. Thank you.